start, so get your coffee and go to your places. Okay, let's start. So it's a pleasure to start the second day of this conference in honor of Ron's 60th birthday. And here he is. And we have, to start very well the morning, David Morrison, telling us about the elliptic Calabi-Yau torsors. David?
Thanks very much. Okay, thanks very much. I'm going to talk today about elliptic Calabi-Yau torsors. I'll explain what that means. And I want to mention that there was a substantial amount of work done on this question about 20 years ago by Grassi, Gross, and Dolgachev. And then it's recently come up in largely the physics literature. So a paper I wrote with Volker Braun in January 2004, a paper with Waddy Taylor in April 2014. That says 14. 2014. Then a very nice paper, which I'm going to call Donaghy et al., although he's not the first author. And I'll describe the example that's discussed in that paper in some detail. And then a more recent paper with a large crew about a slightly different topic, which ended up having an example related to this. And it was actually in the course of writing this most recent paper that I realized that there was a little gap in our understanding, or excuse me, in my understanding of what was going on. I think Mark Gross probably understood from the beginning, but I took a while to catch up. So the talk is about elliptic fibrations. And I'm going to make a distinction that's a linguistic distinction that number theorists often make, and discuss genus 1 fibrations rather than elliptic fibrations. The difference between a genus 1 curve and an elliptic curve is that an elliptic curve has a chosen point, which is used as the origin for the group law. But if you're studying genus 1 curves over fields that aren't algebraically closed, then there might not be a point, and so there's a difference between genus 1 fibrations and genus 1 curves and elliptic curves. And similarly, my genus 1 fibration is going to be a map from an algebraic variety to a base whose general fiber is a curve of genus 1. And if the map has a section, if pi has even a rational section, I'm going to call it an elliptic fibration. And if there's no rational section, well, if it's an algebraic variety, there had better be a multi-section of some kind. And a little argument using the group law of the fibers shows you that the degrees of multi-sections are multiples of some fixed degree. There's a sort of fundamental multi-section. But in that case, I'll just call it a genus 1 fibration instead of an elliptic fibration. Now, one thing we can do is we can consider the corresponding curve, C, over the function field of the base. So that's a genus 1 curve over this particular non-algebraically closed field. Again, the existence of a rational section is precisely the statement that there exists a point on that curve, and so I would call it an elliptic curve if there were a section. And working over arbitrary fields, there's a fundamental association of a curve to its Jacobian, which is an elliptic curve. So there's a canonical marked point on the Jacobian corresponding to the trivial line bundle of degree 0 on the curve. This works over non-algebraic closed fields, and in particular over function fields. So we have this notion of the Jacobian of a given curve over a field. Now, there's also a Jacobian fibration. And constructing a Jacobian fibration is perhaps a little bit tricky. So there is a construction essentially due to Kähler in the case of surfaces and extended by others to a higher dimension, which uses Hodge theory in an essential way. And there are also algebraic constructions. The Hodge theoretic one, how does it go? We have a family of genus 1 curves over the base, so we can look at a classifying map into a space of Hodge structures, E into the space of Hodge structures, and then over that space of Hodge structures we can build a family of elliptic curves. You have to be a little bit careful. In particular, you have to be careful about what's happening at singularities. And Kähler had a rather beautiful theory of what he called the functional and homological invariants for a family of elliptic curves. And from those invariants, which can be read off of the original fibration, you can reconstruct a fibration that actually has a section. So from this point of view, all I'm saying is that I've got my model over the function field of B, and there's a way to make at least a birational model of the thing over something birational to B, and I'll be a little bit more precise about what bases we can take under what circumstances in just a moment. Now, number theorists are fond of the following question. It's important because they would like to be able to study Diophantine equations, for example, which are not necessarily equipped with a point, but the genus 1 fibrations as well. And the question is, given an E, which is an elliptic curve over a field, classify all C's such that the Jacobian of C is isomorphic to E. And actually, as was pointed out very clearly, and this is one of Ron's important contributions to the recent progress, as is pointed out very clearly in this paper of Ron and company. In fact, what we're classifying is isomorphisms. So the distinction between being isomorphic and classifying the isomorphism is an important one. And this turns out, surprisingly, to form a group. So the set as such is a group. And in this generality, it's often called the Weil-Chatelet group. Of the elliptic curve. So I want to do a similar thing if I'm studying elliptic fibrations. By the way, why am I so interested in these elliptic fibrations? There are applications in physics. That's what these papers are about. The application is called F-theory. And when I get to some examples, I will discuss how this why this question is important in F-theory, and how the examples that I talk about are related to things that have been going on in F-theory recently. So, from Kähler's complex analytic point of view, the important thing to handle if you didn't have a section was the notion of multiple fibers and what's called a logarithmic transformation. So Kähler gave a local complex analytic description of a logarithmic transformation where I have some, say, one parameter family of elliptic curves. So there's a section here. And I do a funny thing. I do a base change in the, I extract an mth root with a base change. So I take t is s to the n. And then, so this gives me a family over, okay, I'm going to try to draw the covering thing, family over a branch cover of the original disk, and then I take a quotient, so I still have a family here, and I take another quotient in which I act now not just by the covering transformation, so x and t will go to x plus 1 over m using a point of order m in the group law, together with omega times s, right? This is s. So I take a different quotient, and that different quotient has the effect of piling up the translation only on this central fiber, and it turns out to be non-singular. So in fact, it's fixed point free, as you can see from the way that I wrote down the action. So the question for elliptic surfaces becomes, when can you do logarithmic transformations like this? There are some subtleties to it, but there are some familiar examples. Just to remind people with some classical algebraic geometry experience what the familiar examples are. The first is that the Enrique surface is a log transform of a rational elliptic surface. Enrique surface famously has two double fibers, and each of them can be obtained by a logarithmic transform from two chosen fibers on a rational elliptic surface. Another classical example is if you take a rational elliptic surface and you do one log transform, you again get a rational elliptic surface. And there's some beautiful classical geometry associated with this construction. We all know that if we take two cubics in the plane, they have 9 base points, but they define a pencil, which is the superabundance phenomenon. There's an extra cubic passing through exactly 9 points if the 9 points are the complete intersection of two cubics, right? And then there's a pencil. But there's a variant of this in which you take a cubic, you take that set of 9 points that are the intersection with another cubic, and then you translate one of those points by an m torsion point on the cubic. And when you do that, it turns out that there is a family of curves of degree 6m with 9 m-fold points. And blowing up the 9 base points gives you the logarithmic transformation in a much more geometric form. 3m. Curves of degree 3m. There's a whole pencil of curves of degree 3m with 9 m-fold points. This phenomenon of if you're given the elliptic fibration with section, how do you describe the ones with multiple fibers? For surfaces, Kähler has some analysis of that. There can be continuous parameters, in fact, in the family of things with the same Jacobian fibration. Multiple fibers are not the only thing that happens. You can actually lose the section without encountering a multiple fiber under certain circumstances. So I want to take this to threefolds, and as I mentioned on the first board, the fundamental work here was done by Anton Alagrassi and Mark Gross back in the early 1990s with some collaboration of Igor Dolgachov. And the idea is to combine what we now know about birational geometry of threefolds with questions about elliptic fibrations. So I'm going to use Mori theory to state the results. And in particular, I'm going to consider classes of singularities which are canonical singularities of threefolds. And if I have a variety X with canonical singularities, which is Gorenstein, and Kx is 0, we'll call that a Calabi-Yau threefold. So allowing all those singularities is maybe slightly unusual, but it's important for thinking about the minimal model program. Of course, when I construct the actual minimal models, I restrict to a smaller set, which is the terminal q factorial singularities. And that would be if X were a minimal model. And if I've got an arbitrary algebraic threefold, which is birational to a Calabi-Yau threefold of some kind, then it's known that there is a minimal model. The minimal model will have trivial canonical bundle, and it will only have terminal q factorial singularities. So in this situation of having now a Calabi-Yau threefold with an elliptic vibration to a base, here are the key, sorry. Also, on the base, I'm going to end up with singularities of pairs. So the base is going to have a particular Q divisor on it, which is associated to the canonical bundle of the total space in this situation. And there's a notion of so-called log terminal for such a pair. So that'll show up. So what is Morey theory going to tell me? Well, it tells me, first of all, if X is Calabi-Yau, then there exists a minimal model of X with only Q factorial terminal singularities. What I'm interested in is a case where my Calabi-Yau threefold has an elliptic vibration. So it has, a genus 1 vibration. So it has a map to a base whose general fiber is an elliptic curve. And now let me state what the results are. The key thing is that by doing things carefully, you can make the birational geometry of the total space and the birational geometry of the base match up in some appropriate sense. So here's what you get. So starting from X to B, we produce three things. We produce three models. The first one is X bar to B bar, where this is a minimal model of the total space. And this map, pi bar, is equidimensional. Same thing as flat. So it's quite possible to have an elliptic vibration in dimension 3 and to blow up a point in the total space. Well, if you blow up a point in the total space, you'll destroy the Calabi-Yau nature of the singularities. But in the context that I'm looking at, you might have had a canonical singularity that was isolated, and you might have been able to do a partial resolution of that canonical singularity, which created a divisor mapping to a point in the base. For the study of elliptic vibrations, it's really useful to know that there are models that don't have that property. So there is a minimal model in which it's equidimensional. The second fact is that the Jacobian, J of X, has a minimal model with the same property. Oh, and I should have said, and B bar has only AN type singularities. The Jacobian has a minimal model, J prime over B prime, which is equidimensional. And B prime is non-singular. And there's a map from B prime to B, which is a partial resolution of singularities. So there's a slight mismatch between the birational geometry of the original genus 1 vibration and the birational geometry of the Jacobian. And then the third point is that the Jacobian also has a Weierstrass model. So geometrically, the way we describe Weierstrass model is you contract all components of fibers not meeting the given section. But in fact, that also has a description in terms of a Weierstrass equation. So if you have a model, birational model, in which you've done what I just said, contract all the components of fibers not meeting a section, you can write it in the form y squared equals x cubed plus fx plus g, where X, Y, F, and G are sections of appropriate line bundles over the base. And so I'm just going to call that W prime over B prime. The Weierstrass models that we're looking at have canonical singularities in the total space. So they are still Calabi-Yau threefolds, according to my definition, but they're relatively singular ones. Yes? No, I'm sorry. The X is working over the complex numbers. So X is a threefold over the complex numbers. J prime, well, J of X, I don't think I described how to get a model over the base for the Jacobian. So I described the Jacobian fibration generically by taking the Jacobian of the generic fiber. And the claim is that there is a minimal model over a base which is a resolution, I don't know why I said partial, which is a resolution of singularities of B. So, as I mentioned, I'm going to be discussing some connections with physics. So, I want to bring in one aspect of the physics point of view. And that is that a Calabi-Yau threefold is more than just a complex structure. So, we all know this in algebraic geometry. We know that there are, over the complex numbers, that there are ways of measuring sizes of things, but we generally ignore it. So size matters. Sizes matter. If you have a Ricci flat metric on X, that determines various areas and volumes of algebraic subvarieties. And one way of describing the area and volume information is by means of the Kähler class. So again, just working in algebraic geometry, we're very happy working with the ample cone of ample divisors on this thing, and we can approximate the actual areas and volumes that might show up by rational values. That's great. But really, the physics point of view is that we should be studying not just the variety by itself, but also trying to learn something about what the possible Kähler classes are. And so I point out that I should have said, one of the unknown things is whether a Calabi-Yau threefold has only a finite number of minimal models. It's known that minimal models differ by generalized flop transformations, by things which are isomorphisms in codimension 1. But it's not known that it's finite. So, for example, this series of ideas was used by Mark Gross to prove that the set of birational families of Calabi-Yau threefolds is elliptically fibered Calabi-Yau threefolds is a finite set, but because we don't know about the finiteness of minimal models, we don't know. But we can map out what's happening with various minimal models by using appropriate Kähler classes. So it turns out that if you look at the Kähler cone or the ample cone of one of these Calabi-Yau threefolds, then typically it will have some kind of walls which can be crossed to find a different birational model. So here are the possible areas in one guy. We do a flop by shrinking some curve. We analytically continue that flopping transformation over to the other side, and we discover that the two Kähler cones sit side by side. So the notion of Kähler class that I want to study here is one in which I look at all of the birational models together. I piece together their Kähler cones by using the proper by using pullbacks from H2s by these codimension 1 isomorphisms, which establish canonical isomorphisms between the H2s, and I get this larger cone of possible values. Now, we're studying a fibration, and of course there's a natural sense in which any algebraic class on the base can be thought of as an algebraic class in the total space. In the case where I don't have a section, I use a multisection to find the appropriate class and then divide by the degree of the multisection. I still get a well-defined class. So some of the Kähler classes, some sizes, come from B. And some come from fiber components. And one from the area of the general fiber. So that's the basic supplementary data that I want to use when I discuss these things. In particular, although B and B prime are birational to each other, I will think of B as a specialization of Kähler values. Namely, I've got the exceptional curves for this resolution of singularities. Each of those has an area, and if I tune all those areas to 0, then I end up with the singular model. That singular model, even for the Jacobian, just produces, so it's you end up with canonical singularities in the total space, having done those kinds of contractions, and so that's pretty harmless. We end up with a Calabi-Yau manifold with Calabi-Yau variety with canonical singularities, and that's the one that we want to associate most naturally as being the Jacobian of B. In other words, what I would say is there is some kind of Kähler moduli space going on. So I have the Kähler moduli space of B prime, which is part of the moduli space. And then I'm going to have a specific value. And at that specific value, I have this option of doing the twisting, the analog of logarithmic transformation, or whatever it is, the twisting procedure, which produces the genus 1 fibration. So a genus 1 fibration will typically emanate from a particular point in the Kähler moduli space. And I'll have, at that point in the Kähler moduli space, more than one possible choice of complex structure associated to the same Weierstrass model.
Dave, I'm
Yes.
lost.
Okay.
Looks like to me you were talking about constructing curves in the threefold rather than Kähler classes in the threefold.
Well, I'm identifying Kähler classes by their intersection, or the integral over curves. So I'm using the curves as a set of coordinates on Kähler classes.
But then you need a whole basis, right?
Yeah. If I have, sorry, there's a curve describes a functional on the set of Kähler classes. So the Kähler classes which make sense on B are a subset of the Kähler classes which make sense on B prime, because I had to send all those areas to 0. So that's a coordinate-free way of saying it. Okay, so the starting point is going to be a Weierstrass model. And from the Weierstrass model, I can recover things like J prime over B prime via varying the Kähler parameter. As I mentioned, it's a similar sort of thing, but now in the fiber. The Weierstrass model has canonical singularities in the fiber. I said I was going to obtain it by contracting to 0 size all components of fibers which didn't meet the section. And again, that's a condition on the Kähler class. I want the Kähler class evaluated on each curve in such a component to be 0. And that ends up implementing the birational blowdown from the Kähler or symplectic perspective. Starting from the Weierstrass model, I can turn on all of these Kähler parameters associated with the blowup. That's one thing that I can do. But I could also need to look at this Weierstrass group of W prime over B prime or J prime over B prime, which is the set of possible genus 1 fibrations whose Jacobian is the given guy with fixed Jacobian. And that's what I would like to understand better is what genus 1 fibrations I can get. Okay, so there is another group that number theorists look at called the Tate-Shafarevich group. I'm going to write it with, again with respect to the Weierstrass fibration. It's really defined initially in the function field setting. And in the Tate-Shafarevich group, you look for those twists, those curves, or rather fibrations whose Jacobian is the fixed fibration, which are locally trivial. So there's supposed to be local sections for each guy. And through a misreading of the literature that I committed in January 2014, I identified this as the group that we actually wanted. And without realizing that Mark Rose had carefully pointed out that the Tate-Shafarevich group, as defined by number theorists, which is what he and Dolgachev had been studying, was inadequate to completely describe the elliptic Calabi-Yau torsors. So somewhere in between here is the elliptic Calabi-Yau torsor group, ECT. I don't propose that as a permanent notation, which we're not going to allow all possible genus 1 fibrations because, as in the case of the examples I gave for elliptic surfaces, in many cases the triviality of the canonical bundle would be destroyed, but we have to allow something more than the ones which are locally trivial, so that near each fiber there's a local section, even though there's no global section. So I apologize for having made that mistake. It's propagated into the physics literature with imprecise definitions, sufficiently imprecise that you don't really notice that distinction.
Probably not the first time this has happened.
No, it's absolutely the first time. Yeah, it's never happened before. Okay, so I want to give some examples. To try to explain better what's going on what some of the issues are. Sorry. Before erasing that board, I wanted to point out the role of the singularities in the base of the equidimensional minimal model. So I had X bar to B bar, which was the equidimensional minimal model. I do apologize because when I wrote B prime to B, I meant B prime to B bar right there. Okay. So maybe this should have been a bar or something. Forgot I put the bars for the minimal models. So if I start with an equidimensional minimal model like that, X bar to B bar, the singularities of B bar correspond to multiple fibers. So one of the problems is that if you have multiple fibers in codimension 1 on the base, which is the only thing that you might have for an elliptic surface, then there is a contribution to the canonical bundle of the total space from the multiple fiber. The multiple fiber gets a coefficient like m minus 1 over m in the canonical bundle, and that's incompatible with having trivial canonical bundle for the total space. So we can't allow And the Weierstrass group, by the way, would allow those things arbitrarily. So we can't allow multiple fibers in codimension 1, but we're not forbidden from having multiple fibers in codimension 2. And it turns out that when there are multiple fibers in codimension 2, and you find that equidimensional minimal model, it necessarily has singularities at the locations of those multiple fibers. So that's something which we stumbled upon in this recent paper. I would name all the authors of that paper. There are 7 of them, except I'm being videoed, and I might skip one, and that would be embarrassing, so I won't, but one of my colleagues is sitting there right next to John. Here's a global example which is inspired by the local constructions of that paper. So I start with an elliptic fibration over P2, and I'm going to put it in the following form. I'll write y squared plus, so STU are going to be my homogeneous coordinates on P2. I'll write y squared plus a cubic in STU times xy plus a degree 9 in STU times y is equal to x cubed. And as many people know, this is a trick for guaranteeing that there is a section of order 3 in the Morrison group, namely in these affine coordinates, it's given by 0, 0. So I've taken a Calabi-Yau with, elliptic Calabi-Yau with 2 sections, the 0 section and a section of order 3. I've moved the section of order 3 to the origin in Weierstrass coordinates in coordinates. And instead of using the normal Weierstrass presentation, you could describe it this way. So I'll take alpha and beta to be arbitrary, except that I want alpha and beta to be invariant under an action of Z3, which takes the homogeneous coordinate STU to omega S, omega inverse T, U, for a cube root of unity. And then I'll take the quotient. Except, because I'm trying to produce multiple fibers, I'll do a translation when I take the quotient. So there are 2 possible quotients. There's x, which is x bar mod, the quotient which acts by translation by order 3 plus a third on the fiber, and then this, I'm going to call this one gamma, this gamma on the base. So that maps to P2 mod Z3. And that P2 mod Z3 has 3 A2 points. There are 3 isolated singularities for this group action. And I also have J, which is, or rather, well, maybe I'll call it W, which is X hat mod. And now I don't do anything on the fiber, but I still act by the gamma on the base. And that's mapping to P2 mod Z3. But what I really want to do is take a resolution of singularities there to get J. And so I should resolve singularities in this case. If I don't resolve singularities, I have canonical singularities in the total space. It's perfectly fine as a Calabi-Yau variety, but it doesn't match the conditions that were being stated in those old theorems of Grassi and Gross about the birational geometry. So I have to resolve the singularities for the Jacobian, but I don't, in fact, cannot resolve the singularities here. So if I try to blow up those singular points and take the pullback of the family over the base, I'll discover that there were multiple fibers. The canonical bundle is all wrong. In fact, X is non-singular, even though W tilde is W is singular, right? So you take the quotient in this case, because of the translation on the fiber, I have a non-singular model. So this is a very key example for understanding how this goes. And as the notation suggests, J is the Jacobian base. So it's similar to the logarithmic transformation construction, although it's happening in codimension 2. In fact, if you blow up the 3 fixed points, you can use a version of Kähler's logarithmic transformation to relate those 2 models together, and then maybe blow back down to to get the model that I'm talking about. Example B. So example B comes from the two papers that I wrote in 2014 that I mentioned at the beginning. In example B, I want to consider x over b with a two-section or a bisection. Now, one of the approaches to obtaining a Weierstrass model, one which a lot of us are familiar with, uses the Riemann-Roch theorem on the section and its multiples, thought of as points on this curve over the function field. And Riemann-Roch theorem, which works even in non-algebraically closed settings, tells you that there is a unique section for one time, sorry, a unique global section of the bundle associated to one time the zero section, two sections for two times the section, and so on. Out of that, you build the x and the y, and you discover once you get up to 6 that you've got an equation. There's a similar argument here, where you have a degree 2 point, degree 2 divisor, excuse me, on a genus 1 curve. And given a degree 2 divisor on a genus 1 curve, you run through the same argument, and you discover an equation of the form y squared equals c0 x to the fourth plus c1 x cubed, and so on down to c4, where the cj's are section, and also x and y, are sections of appropriate bundles. Bundle base. All right. Y squared. Y squared is a quartic. Right? So, so if you have, instead of y squared as a cubic, I have y squared as a quartic. I'm not allowed to make it monic in this case. But what I can do is fix a particular two-section and put that at x equals 0. So, in fact, it's okay to have a 0 constant term there if I have a particular two-section fixed. So here is a family of, and it's not hard to work out the conditions on those bundles to make the total space be the Calabi-Yau threefold. So I'd like to kind of run this program here. And to do so, I need to calculate the Jacobian. Well, the Jacobian will be some thing in Weierstrass form, right? It'll be a resolution of the Weierstrass equation. So there's a y squared equals x cubed plus fx plus g, different x and y, sorry. And f and g are somehow functions of the coefficients c0 through c4. So this problem of how do you figure out the Weierstrass coefficients f and g from the coefficients in a quartic is an old one. There are known formulas, there are even versions of the formulas which work in characteristic P. They trace the history back to Hermite at some point, and the formula has been rediscovered a number of times. I want to just mention one feature of the formula which I think is very cute, which helps me derive it, although you can't prove it this way, but you can at least sort of understand what it's doing. And that is to consider the Galois theory of a quartic, c0 x to the 4 plus down to c3x. And I'll put the constant term back in for this little discussion. So many of us have taught this in algebra classes, right? The Galois theory of the quartic is based on the symmetric group S4. And it was this great achievement of the 17th century to find solutions. Exactly who found what and who stole what from what is another story. But to find solutions generally. And the solutions, the closed form solutions in terms of radicals are based on the fact that there is a cool exact sequence in which there's homomorphism, from symmetric group on 4 letters to symmetric group on 3 letters with kernel Z2 squared. And the homomorphism takes an action on 4 points and acts on the 3 ways of dividing 4 points into 2 pairs. That's the canonical way to describe the action. Well, the way this translates into the 17th century solution is that there's a notion of a discriminant cubic, or a it's called a resolvent cubic, whatever it's called, of the original quartic equation. And among other things, the resolvent cubic has the property that its discriminant is the same as the discriminant of the original quartic. So it turns out that that's what this Jacobian is doing. It's finding the resolvent cubic for this quartic polynomial. And if you know that that's what it's doing, you can use a little exercise from undergraduate Galois theory to work out what the formula is. The formula is not pleasant, but you can work it out. Anyway, that's the sort of thing that we're doing. And there's some interesting algebra involved with it. Okay, so if you specialize the equation, you can find a limit of this equation in which you can find an x naught, say to b naught, in which the 2 section splits into 2 sections. So there's a way of comparing this sort of very general case of an elliptic guy with a 2 section to a more special case where there is actually a pair of sections. And when you do that, So when you do that, you discover something about some of the singular fibers. So there are singular fibers, isolated singular fibers in this fibration that consist of a pair of curves, something that looks like, a pair of curves with 2 intersection points. Something that looks like what's called an I2 Kähler fiber, but these are happening in codimension 2. And the typical thing that's happening with the 2 section is that one branch of the 2 section is meeting one of the curves, and the other branch is meeting the other curve. But when I've specialized into 2 different sections, then one of the sections can meet one of the curves, the other section can meet the other curve. Those curves become distinct classes in homology, and in particular, there are choices of Kähler metric which are available when I've split into 2 sections, which distinguish between those 2 curves. So I want to show you a picture of the sort of family of moduli spaces, which I get this way, which I prepared in advance. Not that it's such great artwork. So here I have my my Jacobian family. I'll describe the deformation theory in just a moment. The red circle represents the possible values of this extra Kähler class. So if I'm at a locus, which is represented by this red dot, at which I'm looking here at the Jacobian of the guy with a section, or here at the guy with, a pair of sections, here at the guy with the pair of sections itself, I have this extra class, which is not available when I deform, to distinguish the 2 sizes. And there are 2 circumstances under which you can imagine deforming the resulting guy, 2 sort of reasonable circumstances. One is the one I just mentioned, where the areas of those 2 components are the same. If the areas of the 2 components are the same, then it's, in fact, exactly the situation I've been describing here, where the pair of sections can now deform to just become a more general two-section. And that's what's represented by this yellow curve. On the other hand, if I take the Jacobian, it turns out that from the point of view of this pair of curves, one of the curves has become zero size, and the other curve has its size match that of the general elliptic fiber. So that's the other place where I can do a complex deformation. And when I do the complex deformation, the set of Jacobians always has so-called conifold singularities, ordinary double points, which are the images of those points that I described. And of course, the ordinary double points can be further deformed. So it's possible to deform the Jacobian of the fibration away from this locus where you'd be able to get the twisting. And it's also possible to see that if you use the Kähler parameter, the original family and the twisted family are related to each other by a variation of Kähler parameter at this particular point. But that connection goes away when you move away from the point. Okay, that's a slightly complicated picture, but this picture turns out to very beautifully match the physics. And that's what Wadi Taylor and I showed in April 2014. Namely, in the physical, okay, so I really am not, I'm trying not to do F-theory here, except it's always in the background. So in F-theory, I take the data of the Weierstrass vibration, and I associate in the case of a Calabi-Yau threefold, I associate a six-dimensional physical model, and the key data is the Weierstrass vibration. In such a Weierstrass vibration, it's known that having abelian gauge symmetry, so to have a so-called U1 abelian group, abelian gauge symmetries correspond to elements of the Born-Delvey group of the vibration. This is the Jacobian vibration that I'm discussing. So having that extra section, which is the hypothesis I made upon specializing my complex structure, having that extra section gives me a U1 gauge symmetry. And there's a nice thing that you can do in physics, which is you can apply what's called the Higgs mechanism. And in this particular case, the things that are being Higgs leave you with residual Z2 gauge symmetry. It's the same Higgs, right? Okay, it's the theoretical treatment of the physical phenomenon that was famously finally observed in Nature a few years ago. And this is some kind of deformation of complex structure, typically, to break the U1 gauge symmetry to a Z2 gauge symmetry. Now, discrete gauge symmetries in F-theory are important and also very hard to understand. We have a clear understanding of the abelian gauge symmetries. The non-abelian gauge symmetries come from the types of singularities that show up in the elliptic vibration. But the discrete symmetries are more challenging. And in fact, a long time ago, I argued that the discrete symmetries essentially are the elliptic Calabi-Yau torsors of J over B. Although I wasn't using that language at the time. And the reason is that when you have a gauge symmetry in a physical theory, and you compactify that theory on a circle, well, the picture in F-theory is that when you've compactified the physical F-theory on a circle, you end up with what's called M-theory on the total space of the vibration, although obviously you have to specify the additional parameters which show up when you look at the total space. One of the things that can happen if you have a discrete gauge symmetry is that you should get completely distinct physical theories one dimension down, and since those are supposed to be given by compactifying M-theory on Calabi-Yau threefolds, there should be some finite collection of Calabi-Yau threefolds corresponding to this group. And luckily, the number theorists have taught us that this Weierstrass type phenomenon, or Tate-Schaff-Radich phenomenon, actually forms a group. So we end up with a group there. So the picture is that there is a U1 gauge symmetry which is happening right at this pink point, and the extra parameter that you get in the family of theories is represented by the pink circle. The reason it's a circle is that I'm measuring the relative size of those two components of the given fiber, but the overall fiber size is being fixed in my picture. Really, I should put in another parameter, which is the fiber size, but I suppressed it for clarity. Then, if I specialize, I'm supposed to be getting a Z2 gauge symmetry, and that's represented by this yellow curve, where you see the conifold points that correspond to the Z2 gauge symmetry when there's a section, or you see the whole family that I've written down here when there's not a section. And then, in the case that I was in the fundamental component, I could deform further, although I'm not able to deform further in the presence of this non-trivial Z2 flux around the circle, a Wilson line around the circle. Okay, sorry, that was some physics language, but there are some people who can relate to that. And so the last thing I want to say is Denagi's example. So more precisely, Spanish, Denagi, Paragua, Clevers, and Parechka, in alphabetical order, which I didn't do. And that's to do a similar thing for cubics. So if I take now x to b with a 3-section, then again, there's going to be a model which now looks like a bunch of coefficients times a bunch of cubics in 3 variables. That's the best you could do. And by insisting that all of the cubics pass through a particular point, you end up with a marked 3-section, and blowing up the ambient P2 of the cubics at that point produces a nice Del Pezzo surface, which becomes the ambient space in which the family of elliptic curves lives. And so Denagi et al. Worked out an analog of this picture. Again, from a physical perspective, if you specialize the coefficients so that you actually have 3 sections instead of a 3-section, then you end up with a U1 squared, and the picture is a little more complicated. So there are various relative sizes of fibers, and it's even more complicated. The thing which they had to figure out was that it's still true that the relevant singular fibers in the fibration have 2 components each, but somehow we have, instead of just identifying 2 different limits, we would like in some sense to identify 3 different limits, and so they have to do some interesting birational geometry to get there, but in the end they end up with a similar picture where they're able to relate an element of order 3 in the ECT group to the geometry of these cubics passing through a singular point. So I don't have enough time to give that proper treatment, but that's also, that would be my example C, I guess, where we understand pretty well something occurring in that group. So both examples B and C did not involve multiple fibers at all. Only example A, and the ones I presented, involved the multiple fiber phenomenon. The multiple fiber phenomenon is what pushes you beyond the number theorist definition of Tate-Schaffer-Image group, and we need techniques for evaluating the Tate-Schaffer-Image group itself, and also for evaluating these extensions involving multiple fibers. At the moment, we don't have general techniques. I mean, we have theorems which tell you that they're finite, which is great, but we don't have computational methods for figuring them out. And because our physics friends would like to know about these discrete symmetries, we need those computational methods. So that's on the horizon. I'll stop there.
Any questions?
Right.
So you have these 3 groups, the Modular, the Tate-Schaffer, and in between.
Right.
Could you just do a little table, what's the difference, like which example belongs in which of the three?
It wasn't Morrison, it was Tétchov range. Morrison is yes. So, right. So if I have Birational, ECT, and so this contains this contains Tétchov. So the examples with the degree 2 and degree 3, the 2 section and the 3 section, the examples B and C belong here. Okay. Here was example A, the one that I wrote down with the multiple fiber. And here I would consider multiple fibers in codimension 1 on the base, like an equal surface. So those have to be excluded. I don't know if that's all that has to be excluded. I suspect it's all that has to be excluded, so I'm not going to say that that's exactly the definition of this guy. The definition is that there is a Kähler. Yes?
What? I have no familiarity with the field. What is the size of this group? Are they discrete, positive dimensional?
So these are discrete groups. The Tétchov, for the Calabi-Yau case, the Tétchov-Ravitch group is known to be finite, and this ECT is known to be finite. Marcos has a rather indirect argument. Sorry. He proves that a certain group which is larger, which may be larger than this, is finite. He does not prove that every twist from his group has a Calabi-Yau, is Calabi-Yau trivial canonic on the Birational.
So is there some kind of, the whole modular space of the elliptic Calabi-Yau is some kind of large cover or something?
Well, modular space in elliptic Calabi-Yau, again, I want to put in these Kähler moduli, because here I sort of had two components of complex moduli if I were fixing the Jacobian. Namely, I had the 2 section, and then I had the Jacobian of the 2 section and its deformations, right? So I could only do the twisting when I had specialized the complex structure. But rather than seeing this as some kind of embedded, schemey thing in this space, I point out that physics wants to keep track of this additional parameter where you see how they fit together. Just for completeness, I should mention that there's one more parameter in the physical theory which I didn't mention, which is the choice of a point in the intermediate Jacobian of the Calabi-Yau frequency.
Any other questions? Well, thank you very much.